In this lesson, we are going to talk about rational functions and their graphs, and then talk about characteristics of these functions and their graphs. So, some things to know about the domain of rational functions and just some general information about rational functions. This is what a rational function looks like. Okay, so we worked with simplifying rational expressions earlier this semester. So remember, a rational expression is a function where we have a fraction and we've got something on the top and the bottom of that fraction. Okay, so 1 over x we can think of kind of as our most basic rational function. Okay, the graph of that function is over here on the right side of the screen. Okay. Some things to just kind of know about rational functions is they have what we refer to as asymptotes. Okay, so there are asymptotes on this basic graph at our axes. Okay, so these dashed lines that I'm drawing in represent two asymptotes, one horizontal, one vertical. Okay, both are at the axes, so we have one, let me color code. So this vertical one, okay, and then we have a horizontal one. Okay, so the horizontal asymptote we would write as x equals 0. Okay, so we write it like we would a vertical line. Okay, the horizontal asymptote is at y equals 0. Okay, and what that means, notice in this function, okay, we are getting close, okay, to the asymptotes. Okay, this kind of red graph is getting close to the horizontal and vertical asymptotes. So here it's getting close to the horizontal, here it's getting close to the vertical asymptote, and then same thing for that portion. So rational functions, okay, approach these asymptotes as our function goes out to negative infinity and infinity. So negative infinity is this way, infinity would be out that way. Okay, so notice we're approaching that horizontal asymptote as our function gets really small and really big. Okay. We also, at this single x value, are approaching positive infinity and then approaching negative infinity. Okay. And what'll happen is we're never going to cross these lines. Okay. So we're never going to cross this vertical asymptote. We're just going to get really, really close to it from the left. Okay, so from the left, we're going down to negative infinity. And then from the right, we'll get close to that line as we grow really high, but we won't quite ever touch it. So because of those asymptotes, we have these values for our domain and range. Okay, so the break, the kind of gap right here, okay, in our domain, notice we include every single x value except at x is 0, okay, because x cannot equal 0 in our domain. Same thing here. Oops. Okay, y cannot equal 0, so that's why we kind of have that jump, okay, between negative infinity and infinity. We have that gap where we can't equal 0, so we jump over it when we write out our range. Okay, so your vertical asymptotes impact your domain, okay, and then your horizontal asymptotes impact your range. Okay, so we're going to specifically look at examples of rational functions, and we're going to determine the domain from just those equations. So one thing you can do, okay, when just looking at the equation is you can take the denominator, okay, and set it not equal to 0. So in this case, that is going to be that x cannot equal 0, okay, which is down here. So notice our denominator is just x. We set that not equal to 0, okay, and then we simplify that statement for x as step 2. Notice because this is, again, that basic kind of rational function, it's already solved for x, so we don't have anything else to do. And then we can write that in interval notation, and that gives us the domain. Okay, so again, this is the domain. Okay, and we can find that algebraically without ever graphing our functions. Okay, so just a way to kind of figure out domain from the function without ever graphing it. Okay, so let's do some more practice with just finding domain, and then we'll look at some graphs and find characteristics based off graphs. So when I look at this example, okay, I've got my rational function f of x is equal to 5 over x minus 3. Okay, so here to find the domain, I'm going to set the denominator not equal to 0. So my denominator is x minus 3. I'm going to set that not equal to 0. Okay, that is step 1. Okay, then step 2 is to simplify that statement and for x. Okay, so when I solve that for x, I need to add 3 to both sides, so that'll get rid of that minus 3 on the left. I'm going to be left with just an x, and then x does not equal 0 plus 3 gives me 3. Okay, so what that means is if I can think about my x-axis as a kind of number line, okay, which I have drawn below. Okay, so on the left, I'm going to negative infinity. On the right, I'm going to positive infinity. And what this is saying is that my function's existing everywhere except for at 3. Okay, at 3, I have an issue. We call these discontinuities. Okay, so I'm going to put an open circle there because remember that represents that I'm not at that point. I'm close to it, but I don't exist at 3. So what I do know then is if I think about this in terms of like an inequality, okay, it would mean I exist here and I exist here. So we can think back to when we were working with inequalities, okay, and I can write my answer. All the way on the left, I start at negative infinity, and then I go up to 3, okay, and then I have a union, okay, and then I go from 3 to infinity. So this portion of my interval notation matches this portion of my number line, or you can think about this as your axis. Okay, this portion goes with this portion. Okay, and that is going to be my domain in interval notation. Okay, so again, I can find my domain without ever having graphed this. And again, guys, the reason why we're setting it not equal to 0, okay, I didn't mention this on the last page, is because if I had my denominator equal 0, okay, notice I would get something that looked like this. And we know that we can't divide by 0, okay, so that does not exist. That's an undefined point. So that's why I set my denominator not equal to 0 and solve. Okay, I'm solving for where I could have that issue, okay, where my function would give me an undefined point, okay, and that's going to happen at x equals 3, okay. So that is, again, why we think about this in terms of 0. It's because we can't divide by 0, okay. That causes issues with our domain. Okay, let's look at another example. So this example has a little bit more going on with it, okay. Notice it's got 2 fractions, and it also has some factoring. So we're bringing back all the stuff we knew about factoring, we know about factoring. So before we talk about the factoring, I'm going to look at this first one, okay? So notice this denominator, we cannot have it equal 0. We also can't have this denominator equal 0, okay? So we've got to worry about both denominators, and we can worry about them separately. So I can take x minus 2 and set it not equal to 0. And then simplify here. By adding 2 to both sides, I get x cannot equal 2. Okay, so that's one part where I'm going to have an issue is at 2. All right. This other statement right here, okay, I don't want to set it not equal to 0 yet. I want to factor this, okay. Hopefully we remember our factoring rules. If not, we're definitely going to need to refresh, okay? This is going to be a difference of squares, okay? So remember, if something is two terms, it's either GCF or difference of squares, okay? We know this is difference of squares because x squared is a perfect square and so is 16. Okay, so the way this is going to factor is it's going to factor to x plus 4, x minus 4. Okay, so what I'm going to do is neither of those statements can equal 0 because, again, they're being multiplied together. Okay, so if this statement equals 0, 0 times anything gives me 0 in my denominator. Or if this factor equals 0, okay, 0 times anything would also give me 0. So I'm going to take both pieces, set them not equal to 0, and then simplify. So over here, I'm going to subtract 4 from both sides, so I get x cannot equal negative 4, okay? Over here, I'm going to add 4 to both sides, so I get x cannot equal a positive 4, okay? So I have 3 values where my function doesn't exist, where I have issues. I have issues at negative 4, 2, and 4, okay? So if I think about this on a number line, I've got negative 4, I've got 2, and I've got 4, okay? Those are where I have my issues, and then I exist everywhere else, okay? So my interval notation is going to be a little bit trickier on this one. That's why sometimes this number line is really useful, okay? It maybe wasn't as useful for this one because we just had that one point where we didn't exist. But here it's really nice because it helps us stay on track. So I go from negative infinity to negative 4. I'm going to do my open parentheses, union, parentheses, negative 4 to 2, okay? And then union, I'm going from 2 to 4. Okay, and then I'm doing another union, and I'm going from 4 to infinity. Okay, so I had lots of pieces on this one. Okay, lots of little stuff going on. So if I think about it, this portion goes with this portion of my number line. Okay, this portion goes with this portion of my number line. This portion goes with this portion of my number line. And this portion goes with this portion of my number line. Okay. So again, you do not have to by any means do the number line, okay, for these problems to help you write it in interval notation. But I find that for some of us who are maybe more visual learners, that having that number line drawn out is really helpful when we go to write it in interval notation because it helps us keep track of what's going where and then also the order, okay? Because, guys, if you interval notation is not in this order, say you did like negative infinity to negative 4 union 2 to 4, okay, etc., that is going to be wrong, okay, because these two numbers should always match, okay, when we're doing interval notation for domains of rationals, okay? We can't just like jump from this section of my number line to this section, totally missing the orange portion, okay? And sometimes when we don't do the number line, we'll write things out of order, okay, too. So always good to draw the picture, okay? Okay, so I have 2 that I want you to try on your own. So this is the first one you're going to try on your own. Find the domain and interval notation of this one, okay? So take a second, work through this problem. Okay, so for this one, oops, there's my work. Okay, I took my denominator, x plus 7. I set it not equal to 0 because if it does equal 0, then I've got an issue. All right, so x then cannot equal negative 7. Okay, because to get x by itself, I subtracted 7 from both sides. If I think about what that looks like for my number line, that means I've got an issue at negative 7. Okay, but I exist everywhere else. So I exist below that and I exist above it. And then in interval notation, that's going to look like this. So negative infinity to negative 7, okay, again, is going to be this portion of my number line, okay, and then I've got from negative 7 up to infinity will be this portion, okay. So basically what this is saying is we exist everywhere but at negative 7, okay. So that is number 3, okay. I want you guys to try this one on your own. Now, This one is a little bit trickier, okay, because this one involves factoring, okay? So actually, I want you just to factor this one, and then we'll check our work together, and then we'll come back and we'll do the domain after that. So just factor this one and see what you get. Okay, so for this one, remember when we're factoring trinomials, okay, we need to figure out what two numbers add to the middle number and then multiply to the last number, okay? So here we're multiplying to a positive. So the only way to multiply to a positive is if both our factors are positive numbers or if both our factors are negative, okay? Because we're adding to a negative number, that means both of our numbers are negative here, okay? So when I go to list out my factors for oops, and I didn't mean to write a negative 12 there. Positive 12, we've got -1 times -12, -2 times -6, and then -3 and -4, okay, is my list of factors that multiply to give me a positive 12, okay. From that list, I've got -3 plus -4 is going to add to -7. So those are my factors that I can then use, okay. So take that, okay, and then from there, find the domain. So take a second and find the domain if you haven't already. Okay, so for this one, this is what that function looks like if we rewrite it with the factor denominator, okay. From there, okay, we can take each piece in the denominator, okay. So we've got this piece right here that we set not equal to 0, and then we've also got this piece right here to set not equal to 0, okay. When we do that, we are going to, on this first one, we're going to add 3 to both sides, so we get x cannot equal 3, and then over here we add 4 to both sides, we get x cannot equal 4, okay. From there, we can do our number line, okay. So we exist everywhere except at 3 and at 4, okay. So I exist between, below, and above, okay. So the way that that's going to look in interval notation is like this, okay. And again, this portion of my interval notation goes with this portion of my number line. This portion goes with that little in-between portion, and then the 4 to infinity goes with that one, okay. So that is my final answer in interval notation for my domain. Okay. So I have 2 discontinuities here because I have 2 points at 3 and at 4 where I have issues. Okay. All right. So that's finding domain just given a function without even looking at a graph. We are now going to do some examples where we're given graphs and we're going to find all the characteristics for it. Okay. So I've got the asymptotes drawn in as dashed lines here for us. Okay, so we're going to start with our vertical asymptotes. So remember, vertical asymptotes are written like we do vertical lines. So we're going to start with x equals, okay, and then we got to figure out what x values do I have issues, okay. And notice I've got issues, okay, for my vertical asymptote. I've got issues right here at a -3. Okay, and then I've also got an issue here at +2. Okay, so I can write x equals -3, and you could write this as 2 different lines. Okay, you could also write x equals -3, comma 2. Okay, up to you if you want to write it as one or if you want to write it as 2 separate things. Okay, those are my vertical asymptotes. All right, so now let's look at my horizontal asymptote. So remember, horizontal asymptotes are horizontal lines, so we're going to write it as y equals, okay? And I've got a horizontal line right here, okay, where on the left, okay, so here, and then on the right, I'm going towards this y value, okay? And the y value that I'm going towards on the left and right ends of my graph, okay, is a +1. Okay, so y equals 1 is going to be my horizontal asymptote. Okay, now notice one thing about vertical asymptotes is we never cross a vertical asymptote, never. Okay, we can cross a horizontal asymptote. Okay, that feels really weird. I know it feels weird. Okay, but notice this middle portion of my graph, I do cross that horizontal asymptote. Okay. Now, the reason we can, okay, is because if we think about the definition of an asymptote, guys, asymptotes are what's happening with my graph at the ends. Okay, we're specifically looking at like we call it end behavior. Okay, so for horizontal asymptotes, we're looking at the end behavior. So specifically what's happening as my x values get really small and then as my x values get really big. Okay, so we can think of those as the ends of my graph. Okay, when we're around 0, weird things can happen. Okay, and the weird thing that can happen is that we might cross that x-axis, or we might cross that horizontal asymptote. Okay, so just know that we can cross horizontal asymptotes around the origin, which remember is this 0.00. Okay, so if we're close to 0, okay, x equals 0, we can kind of cross that horizontal asymptote. All right, but then if we're looking at the ends of my graph, we're never going to cross the horizontal asymptote. Okay, so just something weird that happens with horizontal asymptotes. Okay, so from here we can write the domain and range. Okay, so domain, again, I'm going to have issues where I have my vertical asymptote. So I'm going to highlight this in blue because that's where my issues are. So I'm going from negative infinity to -3. Okay, and then union -3 to 2. Okay, and then union 2 to infinity. And I almost ran out of room. There we go. Okay, so same thing as when we were looking at the number line. Okay, I have this portion of my domain goes with like this portion of my x values. This portion of my domain goes with this portion, and then this portion of my domain goes with this portion of my graph. Okay, so that's kind of how those pieces translate onto the graph when we compared to when we looked at them on a number line. Okay, so let's now talk about range. So remember how I told you weird things can happen, okay, and we can cross a horizontal asymptote. Here, we would think that we would write like 1 union 1 to infinity. Okay, now we would do that if this middle portion just didn't exist. Okay, but because that middle portion exists and we do cross the horizontal asymptote, our function exists at every single point. Okay, so again, weird things happen with horizontal asymptotes. Weird things can happen with horizontal asymptotes. So we do cross it near the origin, so my range is going to be all real numbers. Okay. All right, now let's look at my x-intercept. Now my x-intercept is where I cross my x-axis. So it's going to be this point right here, okay, and this point right here. So those points are going to be at -5, -5, 0, and then also at a +1, 0, okay, are my two x-intercepts, okay. I also have y-intercepts, okay, so again, that's where I cross my y-axis, and notice this one isn't quite at a +1, it's a little bit below it, so I'm just going to guesstimate, guys. Okay, do your best. The ones that you're going to do in ALEKS are going to have nice, pretty whole numbers. It's actually really hard to find rational functions that have clean whole number intercepts. I kind of just gave up. All right, so that's why we got some decimals going on. So we're going to guesstimate. Our best guess is it's at about 0.8. Okay, so it's really close to the 1, but not quite there, so that's why we got the 0.8. Okay, so again, when you do your ALEKS homework, it'll be nice, pretty numbers. But for this one, we're going to guesstimate. Okay, so that's finding characteristics based off a graph. Okay, so I want you guys to take a look at this one. I want you to see what you can come up with for the vertical asymptote and then for the horizontal asymptote, and then we'll talk about domain, range, x-intercept, and y-intercept for this one. So try the vertical asymptote and the horizontal asymptote for this one. So for this one, we have just one vertical asymptote, okay, and we then also have our horizontal asymptote. So for that vertical asymptote, if we think about where it exists, it's going to be at x equals, okay, and it's at -4, okay. So that is my vertical asymptote, and guys, that's going to impact my domain. So I can go ahead and do my domain, okay, it's going to be everywhere but at -4. Okay, so that means I need to do this little jump, okay, where I say I'm going to get really close to -4 from the left, and then I don't actually exist at that point, and then I get close to it from the right, and then I go to infinity. Okay, so that is my vertical asymptote in my domain. Okay, my horizontal asymptote, notice, is on the x-axis. So here it's when y equals 0. Okay, so this is an example where I don't cross my horizontal asymptote. Okay, and notice I'm only above it. So my range, my minimum, think range is min to max. Okay, when I'm looking at a graph, my range is from, let me get a color, is from my horizontal asymptote up. Okay, so if I think about how to write that, okay, my min to my max, okay, is going to be from 0. Okay, and again, I'm doing a parentheses at 0 because I don't actually equal 0, because I'm just going to get really, really close to y equals 0, okay, but never actually cross that line or equal it. And then I'm going up to infinity, okay, for my range. And again, remember, infinities always get parentheses. Okay, so that also helps us answer this question about x-intercepts. So we could write an A, or you could write like D and E does not exist. Either or, okay? There is no x-intercept. You could also just write none. That might be preferable for some of you, okay? There's no x-intercept here because we're not crossing that horizontal asymptote in this graph, okay? So no x-intercept on this one, okay? We do have a y-intercept, okay? So we cross the y-axis here at this point, and again, I'm going to estimate here, this is pretty close to 0, okay? So I'm just going to guess that it's 0 point, let's say 1, okay? And that's my guesstimate for that y-intercept. Okay, so that is the characteristics of this graph. Okay, I want you to try this one completely on your own. Okay, so find the asymptotes, find the domain and range, and then the x and y intercepts. Okay, so take a second and work through these questions. Okay, so let's talk about vertical asymptotes. So I have 2 vertical asymptotes. Okay, they exist at -2 and then at a +5. Okay, so I have 2 vertical asymptotes. I have 1 horizontal asymptote. Okay, so this horizontal asymptote exists at y equals -1. Okay, and then from here we can talk about domain and range. So notice my domain has got gaps at -2 and at 5. Okay, and I'm existing everywhere else. So I go from -infinity up to -2, union -2 to 5, union 5 to infinity. Okay, so that is my domain. Okay, my range, remember for this one, I do cross my horizontal asymptote there in kind of the middle portion of my graph. So my range here is going to be all real numbers. So that's -infinity to +infinity. Okay, so this is that kind of special case. My x-intercept, if I think about where that is on my graph, okay, my x-intercept is where I cross my x-axis. So I have a point right here and I have a point right here. All right, so that's going to be at -5 and then a -1. Okay, so -5, 0 is the coordinate, and then -1, 0 is my other coordinate for those x-intercepts. Okay, my y-intercept is where I cross my y-axis, and again, that is right here. Okay, again, that's not at a whole number, so I'm just kind of guesstimating that decimal as being at around 0.5. Okay, and that is my y-intercept. So that is finding characteristics of rational functions, just given the equation and then also given the graph. Okay, so let me know if you guys have any questions about any of that.